Hello and welcome back. So, we have been looking into the application of laser in separating isotopes. So, we have seen that there are several isotopic separation schemes by using lasers, and we have broadly categorized them into 4 different classes. Now, one thing I must tell here, that no separation techniques lead to a complete separation of two products or to any two material under consideration. Similarly, in laser separation technique also for isotopes, it does not lead to completion of the separation. So, what it does essentially is the creation of an enrichment of one particular isotope of interest. So, it creates the abundance of one of the isotopes in much higher amount. For certain applications, suppose one of the isotope is needed, then there is also a limit that if you have this much of relative abundance of isotope 1 over isotope 2, then you can actually process the or go ahead and do the rest of the job. So, this laser separation technique essentially does the same job. They enrich the amount of one particular isotope over another, and then the following applications or processes they take place. So, essentially I should mention that laser assisted isotope separation it generally effect in enrichment of one of the isotopes. For example, if I deal with uranium 235 and uranium 238, then my application may require that I must have more relative abundance of uranium 235 over 238, and my laser separation technique will give me that much amount of relative abundance of U235 over U238, and that is good enough for me, because that is one, I am now able to go ahead and do my job with uranium 235, and second, most importantly, I really did not have any other way to achieve that. Fine. All right. So, let us consider the essential features of this isotope separation. So, one thing is that one must have well resolved isotopic shift in absorption frequency or wavelength, whatever you say. Second, the laser line width must be smaller than this isotopic shift, must be smaller than the isotopic frequency shift, as we said in the first clause. And third is we should have an efficient extraction stage. What does that mean? That whatever the laser do with the isotope, so it will probably give you in terms of a different product having that particular isotope. It can produce that in excited state. Whatever it does, I must have a particular technique to then take out that particular separated isotope, or I must and also I must have a very efficient technique to do that. Okay. So, if I have these three criteria fulfilled, I am ready to go to do the isotope separation using laser. Okay. Now, one important factor here, in this case the starting material and the end product during laser separation may not be identical. But that is not a big deal, because suppose I am looking at this radioactive isotopes. Okay. So, they may be in an atom or they may be in a molecule, they will remain as it is, correct. So, I do not care much about that one. So, I can always get my desired isotope separated. Okay. So, now as I said earlier that they do not lead to complete separation, but they generally affect in enrichment of one of the isotopes, then I must have a way to quantify this enrichment, and that is what is the most important factor used in laser separation technique, and this is called the enrichment factor, which is given a symbol of beta. Okay. So, this beta is defined as or so, here suppose I start with my two isotopes labeled as R1 and R2. Okay. So, my R1 and R2 are two isotopes that I would like to separate out, and suppose after the laser excitation my products are P1 and P2 and N's are their respective number of moles, and if I know the number of moles I can always calculate the mole fractions given by X's. Then this is the relation by which I get the enrichment factor. Okay. Now, looking at the value of beta, I can get that how much relative abundance of one isotope has been achieved over the others. Okay. And a typical number of beta, and you can actually figure out that from this expression that beta must be greater than 1 to have a desired thing, right. If it is less than 1, then I have not achieved any enrichment there. So, typical value of beta, it lies in the range of say 1 to 10 power 4. Okay. So, I will give you one example. So, this example is about the enrichment of uranium, and uranium is used as a fuel in the nuclear reactors. Okay. So, in nuclear reactors uranium 235 is required, and uh, and this is the naturally occurring uranium. Okay. Now, we have a mole fraction that is naturally available of uranium 235 is approximately 7 into 10 to the power minus 3. Okay, when I consider 235 and 238 isotopes. Now, so we require 235 isotope, and not only that, if I want to really be able to use uranium 235 in the reactor, the mole fraction that is required, so required X uranium 235 is approximately 3 into 10 to the power minus 2. Okay. So, this is my requirement, all right. So, now when I do this isotopic separation, so in that case I will get my beta values, okay, with time, and this requirement, and knowing that this is the mole fraction of U235 to start with, I can get what is the beta actually that is needed. So, therefore, the required beta is equal to around 4.3. Okay. So, when this equals to 4.3 for uranium separation, I am ready to go for using that uranium 235 in my reactor as a fuel, and we call that, okay, we have enriched the uranium 235 sufficiently. So, this is one of the very nice example of utilization of isotope separation. Okay, at this point if I ask you, okay, who will be interested in this kind of separation techniques using laser? So, there will be several industries who will be interested, and one of them I do not have to tell you anymore after telling this one. This is one of the really important thing for any government in today's world, right. Whenever you need energy, you go to some nuclear reactor, produce energy that solves the energy requirement for large countries. So, nuclear industry or some related industry who utilizes many of the byproducts in these things, and you can separate them, and then you can use them for further applications in different fields. Okay, so the need of such technique is really vast. Okay. All right. So, now let us quickly go through the different schemes that we talked about. So, we talked about selective photoionization, selective dissociation, and selective photochemical reaction, as well as selective photo deflection. So, now let us look at those things real quick. So, when I talk about photoionization, okay, so selective ionization, so what do we understand about ionization? So, if I have a molecule present in the ground state and they may have some excited state here, and then this is the limit beyond which the ionization will take place. So, this is the continuum. So, I can have, this is for say my atom or my isotope 1, and then I have my isotope 2. Okay. So, the dissociation level and the ground state, they are same. Okay. Now, if I think of the conventional dissociation using a single photon absorption, then what do I have? I have a transition like this when I come with a photon called h nu, and if I do that same thing here, what I will get? I will get the same fate. Okay. So, this is also h nu, and this excess energy for both of them which matches with this will give me the kinetic energy of the ionized product and the electron. Okay. So, now what do I get out of this photoionization? Suppose I have two isotopes, I bring in my laser and I hit it with a photon energy such that one photon will take the system, to the ionization limit. Then essentially both of the isotopes will behave in the same way. So, we have a problem in this case. Now, what I can do? I can do this particular photoionization in two steps. How? So, if I bring a particular energy, say nu 1, which causes a transition between the ground state and this first excited state here, and I have this is h nu 1, and in the following step I have a second photon which takes these molecules to this ionization, beyond this ionization limit. Then what will happen? If A1 has the state such that it matches with this nu 1, and if I use the same laser light to do the same job in A2, it will not work. So, it will work only for A1, it will not work for A2. That is what exactly I want, because here this energy is right for this transition, while this energy is not the right one for this transition, correct. So, therefore, I will not have a transition here, I will not have then a photoionization for A2 if I use nu 1 2. So, this one h nu 2. Okay. So, then I will ionize one of the isotopes selectively. Okay. After I ionize them selectively, what I can do? I can pass these ions through a very strong field. Okay. So, through a very strong field, strong electric field, as strong as say like 10 power 5 volt per meter, then I can selectively collect them, right. So, then I can do whatever the things that I want to do, all right. So, this is a very fantastic scheme where you are using a 2 photon, essentially 2 photon, and also this is a 2-step process. Only thing I have to be careful about is the frequencies that I am using. This nu 1 or nu 2, they should not be such that they themselves they themselves create the ionization. So, my condition will be that H nu 1 or H nu 2 must be less than the ionization energy I, which should be less than the sum of this. This is very easy to understand because nu 1 plus nu 2 is more than the ionization energy. So, this is my ionization energy, right. So, individually nu 1 and nu 2 must be less than that of the ionization energy, while together nu 1 and nu 2 will be more than the ionization energy. So, you use something like a dye laser which is tunable and tune your wavelength to match one of these states. So, that excited states will be different in two different isotopes, because that is what my requirement also says, that the shift in the absorption frequency must be there and they must be quite well shifted with respect to my line width of the laser. And if I have that condition, then I will populate only one of the isotopes, not the other, and hence in the next step I will ionize only that isotope, not the other. So, I have only one ionized isotope product, then separate them using a particular field and then go to the next step, whatever you want to do with that particular isotope. Okay. So, this is one technique that is used in case of isotope separation. There are other techniques, as I said. Second is dissociation. So, this is pretty much like the ionization process, where we took the help of multi-step ionization process, and that is also a kind of resonant enhanced ionization, photon ionization. So, here when we talk about dissociation, what we see, it can be one can excite the molecule up here and that will go and dissociate. Okay. So, this is within the same level, you can do that. Also, what you can do, that you can put over here and the molecule will be dissociating, correct. Now, what you normally do to separate the isotopes, the different isotopes will have their vibrational levels shifted from each other. So, here also if you use a two-step process, in the first step you use an infrared laser having a very long wavelength or very low frequency light, and excite the vibrational level of one isotope only. So, then okay, and if I use a different color in the same scheme to show that okay, the isotope levels, they have different energies. So, the yellow color is for one isotope while the white color is for the other isotope. Then if I bring in an infrared laser which will populate say only the yellow one, then in the next step if I bring an UV laser light and then excite it over here, and then I get dissociation product, and this dissociation product will contain only one isotope, because I am selectively exciting one isotope and the other remaining silent. So, in this way I can do it. Instead of using two photon process or two step process, we can also use a single photon process in certain cases where I have a case of pre-dissociation. Okay. So, for example, if I show it separately, Okay. So, this is a dissociative state. So, if I excite here, I will not have any problem, because this will just come down and at max it can come here and then it can dissociate. But if I excite to say high energy, then the molecule will vibrate in this level and then it will come to this particular dissociative channel, and then I will have a dissociation product along this one. So, in this case, if my isotopic level states are separate in energy such that I can use only one single photon and have a pre-dissociation beyond a certain energy, then I can use a single photon also to do the isotopic separation. Okay. So, the third one is the reaction, which is very well known for many of us. Laser induced chemistry actually plays the role here. Now, by using a suitable wavelength of light, and because this is very narrow, having very narrow line width, one can excite a particular isomer to a particular state while the other remains silent. Okay. So, this has been used a lot in case of separating isomeric products having isotopes as the constituent, and also many occasions it is actually the laser induces an isomerization which then is easy to separate out, and this happens in case of one particular isotope while the other remains silent. And the last thing I will talk about is the photo deflection. So, photo deflection is that photon, when it hits particularly the laser light, it transfers the momentum also. Okay. So, suppose my molecules are moving in this direction, suppose, okay, for example something like in a supersonic jet expansion, and if my laser light it is at perpendicular. So, this is my laser, okay, and this is my molecules or containing the isotopes. Okay. Then what will happen, due to this momentum impart on this particular molecules going here, they will start deflecting. Okay. So, it involves quite a lot of thing. So, we are running out of time today. So, I will finish this part in the following class and then move on to some other topics. Thank you very much.